What is entropy? We'll start with a brief review. We like specific definitions in physics, which is why calling entropy disorder seems so weird. But it works. Gas has more disorder in it than a solid. How can we quantify that disorder? With this equation from Rudolf Clausius. This equation works for reversible processes like the Carnot cycle or the Carnot engine. That's what we found in part 2. We'll review that work in just a second, but this part is mostly about a new and an even stranger equation, but one which Boltzmann was so impressed with that he put it on his tombstone. Now that is cool, or crazy, or both. That's what this video is about, making more sense out of disorder and getting Clausius and Boltzmann to play nicely together. First, a recap quickly of parts 1 and 2. Entropy helps us explain spontaneous reactions, why nature moves in a preferred direction, why heat flows from hot to cold, and we approach these things using the ideal gas processes and equations and an idealized engine that moves through 4 stages. 2 of them isothermal, 2 of them adiabatic. Go clockwise and you are using the flow of heat, hot to cold, to do work, like a water wheel moves with flowing water. But Carnot's engine is reversible. Go counterclockwise and you are a heat pump, using an external energy source to move heat from cold to hot. Either way, heat engine or heat pump, energy is conserved. But, and this was the heavy lifting of part 1, something else must be conserved also in order to make this a reversible process: entropy. Delta Q over T. That was Clausius. Now, Boltzmann, starting with multiplicity. With what? With coins. Right now, they're all heads up. But let's say we flip them all and then we get 3 heads and 1 tails. What are the chances of that? Let's find out. First, why do we care? Well, we're trying to find out why nature tends to increase entropy. That means we're playing the odds. Anyway, there are 4 ways of getting 1 tails. That's multiplicity. The number of arrangements, or microstates, per macrostate. Having 1 tail, that's the macrostate. These are the 4 microstates. There are 5 possible macrostates, from 4 heads to 0 heads. And all the different microstates are equally probable. That's the answer to our question. You have a 25% chance of flipping 1 tail if you throw all those coins together. 2 heads and 2 tails. That macrostate is the most likely. So that's multiplicity, omega, the number of microstates for a macrostate. Now, where does the rest of Boltzmann's equation come from? From this, Clausius' equation with a little help from our expression for Q. Hey, isn't that good only for adiabatic processes? Yes, but don't worry, this system, the coins, are not gaining or losing any heat as we flip them. Now, rearrange using the connection between Boltzmann's constant and the ideal gas law. Avogadro is smiling in the background somewhere. We'll also assign V initial a value of 1, and that way we're getting something like an absolute value for entropy. This is not a rigorous proof, I should admit that. Right now, 1 step left, showing that volume to the n power gives us multiplicity. How can we prove that? Well, we can't prove that, but we'll show you some examples using an egg carton, or part of an egg carton, and 3 colored balls, or maybe just 1 or 2. How many ways could we put 1 ball into 3 spaces? Well, this many. V equals 3, n equals 1. Multiplicity is 3. And I hope you agree that for the entire carton, if V equals 12 and n equals 1, omega is 12. What about 2 different balls into 3 spaces? How many arrangements? 9. The equation works. 1 more. How about 3 different balls spread between 2 different spaces? How many different arrangements? 8 arrangements. 2 to the 3rd power. This equation works again. No, this is not a rigorous proof, and it's not connected with a physical system. That's a problem. How does multiplicity help us understand entropy, like heat flowing from hot to cold, or a gas diffusing? Well, let's consider 5 coins this time. Pennies. 5 quarters, that's too many for me. Here is a very ordered state. Not very likely if you just flipped all the coins randomly. If we take that system, that ordered system, and shake it up, you'd be more likely to get something like this, maybe 2 or maybe 3 heads. Work out the permutations. The 3-tail state is 10 times more likely than the no-tail state. Probability is a thing. Now the analogy. I'm saying that having all the coins in one state heads is like having all the system's energy in one cup. A mixed up system is more likely, and when nature rolls the dice, that's what you'll get. More multiplicity, more microstates, a greater number of microstates associated with that mixed up system, higher entropy. That shows the limit of the first law. According to the conservation of energy, you could take a warm cup of water, recite an incantation, and pour out one cold cup and one boiling cup. You could have an ice cube jump out of boiling water. Total energy would be conserved. The first law of thermodynamics would be satisfied, but not the second. Entropy would decrease, and Boltzmann and Clausius would be frowning at you. That'd be like throwing 100 coins into the air and having them all land heads up. What are the chances of that? Not good. What about a gas? Having all the energy on the left side is like having all the coins on the heads side. A mixed up system is much more probable. But could it go in the other direction? Well, James Clerk Maxwell imagined a situation where a demon, he would have that demon build a wall in the middle of the chamber. And then he'd keep that wall closed, but they'd open a little window if he ever saw a fast particle passing the midpoint moving to the left. Or he'd open the window if he saw a slow-moving particle passing the midpoint moving to the right. Pretty soon the gases would be separated, and again, energy would be conserved. First law satisfied, second law, not so much. So there is multiplicity in a cup of water. It tells heat to go from hot to cold. And if you look closely, you can even see Boltzmann playing nicely with Clausius. How's that? Well, even though the same amount of heat leaves the hot cup and enters the cold cup, the temperatures clearly are different. That means the total entropy of the system increases. Entropy increases, which is just what these guys and all the rest of nature wanted.